Today is our 179th session, talking about recharging cities and update on the electric vehicle charging in the United States cities. The recent high gas price are driving renewed interest in electric vehicle in the US. However, roughly about half of US households do not have access to a home charger. Either do not have a driveway, garage, or access. So we still need a dedicated, reliable, affordable public charging network. We're really glad to have Tiya from It's Electric, Professor Daniel Freund from MIT, and our own Bhuvan, the panelists. And John organized the panel discussion today. We'll leave John to introduce the panel properly. Before that, I want to reinforce the norm of the forum, which is invite everyone to contribute an idea to the forum. The idea could be a question to the panelists or could be a comment to the panelists. You can type directly into the chat of Chief John. Yes.
Super. Okay. Thanks, Jinhua. So, I think we've seen that electric vehicles in the United States have been on a bit of a roller coaster ride, both for consumers and for the automakers. We've seen a clear retrenchment in the market since the $7,500 tax credit expired on September 30th of last year. So we've seen the market share of EVs fall from a peak of about 10% last year to roughly around 6% this year. And my colleague Bhuvan is going to go into great detail on where we are in the market right now. Now, on the automaker side, we've seen also massive, massive investment going into this space. I mean, if you think about just the pure amount of money it takes to shift these car platforms from gas to electric, it's huge investment. And that's also, taken a toll as some automakers had overestimated the demand for where we'd be at electric vehicles right now. There was just an article in the Wall Street Journal yesterday about Honda, which announced a $2.7 billion loss, their first annual loss ever in the history of the company. And that part of that is because they made a $10 billion bet on electrification that didn't quite manifest itself in the market as expected. Now, of course, having said that, as Jinhua just mentioned, we're seeing some renewed interest in electric vehicles with high gas prices, what looks like will be a sustained situation of high gas prices. And we've always been at the belief at the Mobility Initiative that long term, across multiple geographies around the world, the trend of automotive electrification will continue. So we think this is a really important topic, as Jinhua mentioned. Many folks do not have the luxury of a garage or a driveway or a dedicated parking space where they can install a home charger. And so they're reliant on the public network of chargers. And so the question we're addressing today is, what does that look like for folks who live in cities? So to kick us off, I want to turn to my colleague, Bhuvan, who's done a kind of overview of where we are in the EV market and where we are with charging from a global perspective. Bhuvan requires no introduction. Over to you, Bhuvan.
Thanks, John. I'm just getting my screen share. I hope everyone can see that.
Yes.
All right. So around 2008 to 2010 is when in the US the whole 7,500 tax credit was introduced. And so as John mentioned, I'm just going to quickly run through and give a landscape view of what's happening across the US, Europe, and China, both in terms of EV sales and then charging. And then we can move on to the rest of the panelists here. So like I said, 2008, 2010, the 7,500 tax credit was introduced. And in 2022, through the IRA, the manufacturer cap of 200,000 vehicles was removed. This was a big deal because Tesla, General Motors, and Toyota became eligible again. So folks could again buy a Tesla or a Chevy Bolt and avail of the 7,500 EV consumer tax credit. The government added a few restrictions on income, 55,000 for cars, 80,000 for SUVs, for MSRP income, and that the final assembly has to be in North America. And critically, there were 5 billion for EV charging and 5 billion for DC fast charging through the NEVI funds that were earmarked in 2022. In 2023, there was a used EV credit introduced as well for $4,000. A few more restrictions on critical minerals and battery components if you're availing of the consumer tax credit. But there was a leasing loophole, so most restrictions, such as your MSRP cap, foreign made, did not apply for BEVs that were leased. And as a result of which, there was this very interesting trend of EV leases shot up from 16% in the beginning of January 2023 to 80% by mid 2024. So everybody was sort of using the loophole to get the best deal on an EV. So the other significant development in the US, especially, was the adoption of the Tesla plug as the standard, and most OEMs have done this, and most new cars, EVs, BEVs that you buy now are coming with a Tesla plug. And we end 2024, in the beginning of 2024, the 7,500, instead of a tax rebate, you could avail it as a point of sale rebate when you were purchasing the car. Again, great for consumers and great for the uptick of EVs. 2025 saw a change in the federal government in the US. In Feb 2025, the whole NEVI program was paused. The whole, EV charging, the money was paused. In July, the One Big Beautiful Bill Act was signed, which terminated the 7,500 federal EV tax credit 7 years before the original expiration date of December 2032. As a result, the tax credit ended on September 30th of 2025, and people rushed in to buy their EVs. And in Q3 of 2025, we saw the highest BEV sales so far, over 400,000, and 10.7% of new car sales, as John mentioned, were EVs. This is the highest the US has ever seen. But obviously, then the sales came crashing down. And in Q4 of 2025, the sales fell almost by half compared to Q3. And this was the lowest quarterly sales in over 3 years. So just quickly looking at the sales trend, in 2024, there were a lot of news articles saying that, hey, the growth of EVs is slowing down. And while the growth rate had slowed down, it was still a growing market. Every quarter was larger than that of the previous year. This was until Q3 of 2025 when we saw that big spike, and then everything came crashing down. And Q4 of 2025 and Q1 of 2026 were the first time since ever that the sales in a quarter were less than that of the previous year. So this is a significant thing, because then we're actually degrowing, as in terms of sales. Just quickly looking through the manufacturers, the top 7 in the US. This is only BEVs, not not plug-in hybrids, not hybrid electric vehicles. As you can see, Tesla is a major player. The blue is Tesla, but General Motors has been doing fairly well. Ford was doing well, but now they don't have too many models on sale. The F-150 Lightning has been removed from the market. However, Tesla sales peaked in 2023, but have since fallen below 50%. Moving on to a different geography, I just wanted to cover Europe very quickly. Europe is much more ahead of the US, with BEV sales in 2026 hitting 20%. This is, twice the largest peak that US has ever had. And PHEV sales also are at 10%. So plug cars are close to 30% of new vehicle car sales in the US and in Europe, and growing very, very well. By manufacturers, it's a much more diverse set of manufacturers. As you can see, Tesla is the same blue color, but it's less than 10%. And Volkswagen, especially if you consider the group, that's Volkswagen, Skoda, and Audi, is by far the number one player there. And Tesla, again, similar story here, peaked in 2023 with like a 20% plus market share, but now has fallen to less than 10%. And it's a very, very diverse market, and with a very diverse choice of vehicles. You get small EVs, you get SUVs, you get crossovers. And hence the sales also are much, much better. Continuing on the Tesla trend, I put together numbers of Tesla US, Tesla Europe, and an estimate of Tesla China retail sales, which is almost 90% of Tesla global. And as you can see, it's not a good look for the company. The global annual deliveries have fallen in 2024 over 23 and 2025 over 24. And 2026 is not looking great as well for the company, which once was the poster child of BEVs. Moving on to the biggest electric market, which is China. China actually hit 50% of new car sales as NEVs. NEVs is basically BEVs plus plug-in hybrids in China. So any car with a plug, around half of this would be BEVs. So half of, this is 56% of NEVs in 2025 for BEVs. So effectively 28% of new cars sold in 2025 in China were battery electric vehicles. So that's, a very, very healthy trend there. And retail sales, as you can see in China, average 1.7 million BEVs. This is BEVs, not NEVs. So battery electric vehicles are 1.7 million in China. Europe is close to 5, and US is close to 3 million for these for 2024 to 2026. So there's a huge difference here. I just wanted to share this slide here. So this is the top 10 manufacturers of NEVs in China by sales in April 2026. All are Chinese manufacturers. Tesla failed to make it in the top 10. They were at 25,956 and NIO was at like 30,000. So there's a huge gap of 5,000 vehicles. So this is just to say that it's a very different market with very, very strong and excellent products from the local players over there, which and they're competing globally. We just don't see them in the US. Moving to a much smaller market, which is India. India has seen growth in the BEV market, but it's still very, very small. We've seen growth mainly in 2024 and 2025 because of new models, very affordable models launched by Mahindra, Tata, and MG. But like I said, it's still around 4% of new car sales, so even smaller than the US in terms of percentage of new car sales. And in terms of manufacturer, it's mostly homegrown Mahindra, Tata, and MG Motor, which is this is a joint venture between an Indian company and the Chinese-owned MG. So moving to charging, so this is the second part of my presentation, and this will segue into the rest of the talk. So US at the end of March, April 2026 has around 244,000 ports, public charging ports, slow and fast, DC fast charging and level 2. Europe is around 4.6 times that. Despite this, the sales per quarter being only 1.5x, the number of ports is 4.6x, so something to take note of. China is 4.3 times that of the EU, and China is 20 times that of US in terms of public charging ports. Just something to keep in mind. If you look at it, just break it down by country. In the US, 29% are DC fast chargers and 71% are slow. And out of the 29%, half are Tesla. So there's been a 2.5x growth in the public charging ports compared to 2021 in the US. Same thing if you look at in Europe, it's 3.75 times the growth in the number of ports. But Europe has much higher share of slow chargers. It could be a matter of, people are charging where they park. They have smaller batteries because they have smaller cars. Very interesting scenario here. And my last slide over here is China actually has much higher share of DC fast chargers, almost like 45%. And they've actually grown at 4.25 times of their 2021 numbers, which is already a very big number. And just to add, my last statement here, China has 6,000 battery swap stations in addition to this DC fast charger and slow charger infrastructure. So with that, I'll hand it over to John.
Super. Thanks so much, Bhuvan. Okay, let's continue on to the next segment. So I'd like to introduce Professor Daniel Freund. He's Associate Professor of Operations Management at the MIT Sloan School of Management. Dan's research focuses on applied techniques from optimization, stochastic modeling, revenue management, to problems in transportation, online platforms, and humanitarian immigration efforts, among others. Before joining MIT, Dan was a postdoc in Lyft's Marketplace Labs team. Dan and a colleague of his, Alex Jacolat at the Sloan School, collaborated with us on a project that looked at optimization of urban electric vehicle charging stations, did some very interesting work. And if we could turn it over to you, Dan, to share that project.
Thank you, John. Yeah, I'll be presenting some MMI-sponsored work that Alex and I conducted from 2023 to 2025. This was work done together with our research assistants, Julia and Giorgio, who were really leading the charge throughout the project. To give you a high-level overview, the project really involved two main aspects. As a first part, we wanted to develop a machine learning vision-based approach to identify potential sites to install chargers, where we used Google Street View data to identify locations that would be suitable to install a charger, or in the example here, that maybe wouldn't be suitable to install a charger. On the right, you see in the picture there's a fire hydrant. So that's a location where installing a charger would actually require some infrastructure change. And then in the second part, we developed an optimization model to understand how EV charging networks should be structured in urban environments, with a specific focus on the number, location, size, and technologies of chargers. And in particular, one of the questions we wanted to answer in that context is whether we would want, or whether a city should want, to install only level 2 chargers, or level 1 and level 2 chargers, only slow chargers, or only DC fast chargers, or maybe a mixture of both. And moreover, we wanted to understand what drives a city wanting to install a mixture of both. So let me first talk about the first part, the machine learning aspect. We leveraged Google Street View API. We leveraged the Google Street View API to get image data from road segments. So you see on the screenshot in the slide that for various parts of the city, we got screenshots at a quite granular level. We would get 5 images with different angles from a given site. And we would label these by hand based on whether or not they would allow for a charger to be installed. So for example, when there's a bike path, when there is a pathway that goes into a parking garage, when there is a fire hydrant, those are all reasons why it would not be suitable. And otherwise, if there's no sort of obstruction whatsoever, it would be suitable. Now, we leveraged an active learning approach to label, where we prioritized sites where the model expressed greater uncertainty about whether or not it would be suitable. And the key idea that ultimately allowed us to develop a strong machine learning methodology was to leverage an architecture called Timesformer. This is a transformer-based model that is explicitly designed for videos. Now you might say, well, we don't really have a video here, we just have 5 pictures. But if you think about it, the 5 pictures are in sequence, one after the other. They're a little bit like 5 frames of a video taken of a particular site. And it turns out that this Timesformer architecture was much better at predicting whether or not a location would be suitable than other models that we tried. So here I'm showing you in these plots or in this plot how our model accuracy improved from the start of our project when we had few labeled data points and we didn't have this Timesformer architecture in September 2023 all the way to February 2024 when the Timesformer architecture and Giorgio having had a broken hand from a skiing accident that allowed him to spend a lot of time on labeling by hand. Those two came together to drive our model accuracy way up to about 90%. So at that point, we felt like we had a pretty convincing model which could actually be used in practice, as opposed to an accuracy of, for example, 70%. That still means that 1 in 4 locations that you might label, that the model might label as being fine to install a charger would still not be fine. That would be problematic. We also developed an interactive visualization tool that I just want to show here to sort of display how this could be used by practitioners. It displays a map of the city of Detroit. We did all this in the context of Detroit, but the techniques and the software stack would translate to other use cases. and it would display not just the map, but it would display all the locations for which we queried image data. And it would then have in color whether or not these would be suitable. So the green dots on the map naturally are the locations that our model identified as suitable. And one can then click on these dots and see the actual Google Street View perspective of that location. So for example, here it's a point that our location that was predicted by the model as being suitable for a charger. And you can see in the in the street view perspective that indeed there's nothing that would obstruct a charger from being installed there. Now, in the second part of the project, we wanted to use this in an optimization model that that would then actually prescribe where to install chargers. That optimization model consists of two pieces of input. One is a map of the city with feasible charging sites that effectively comes from the first part. And the second is a trip-based travel demand in a metropolitan area. And for that, we used census data. The optimization model is then characterized by the following features. There are customer types that are characterized by the locations at which they can charge, together with the time windows during which they can charge at these locations. For example, if you imagine somebody coming into the city from the suburbs and then being at their workplace, they can charge near their workplace during working hours, but then in the evening they go back home. So in the evening, they would need to be charging closer to their home. So that is what characterizes a customer type in the model. We also have charger types characterized by their cost and their capacity to serve demand. So a fast charger can serve more demand in a given time window, but than an L2 charger. But it also, of course, is costlier to install. And we have limits at locations on the number of chargers that can be installed. For that, we were trying to get Detroit utilities to provide us with maps of how highly the grid is utilized in different parts of the city, which consequently would limit how many chargers could be installed. We ultimately were never really able to get that data, in part because it wasn't static, because the utilities were actually investing in expanding the grid, which meant that they weren't able to give us sort of a fixed capacity for different locations for how much could be installed. Now, writing this formally, our model can be summarized in this integer optimization model here. I don't want to discuss it in too much detail, but it aims to minimize the upstream construction cost of the EV charger sites while ensuring downstream that the demand that we are estimating would be met. And what I want to highlight is just that in this formulation, costs are differentiated by whether the charger that gets installed at a given location is an L3 or an L2 charger, or there can also be multiple chargers installed at one location. But then the cost of an L2 charger throughout is normalized to just be one. And the larger cost of an L3 charger is set to be a parameter alpha. So the alpha up here you can think of as being the multiple of how much more expensive a DC fast charger is compared to an L2 charger. With that formulation in hand, we obtained both some theoretical and some data-driven result. The first theoretical result is that if you consider one fixed location and you're deciding whether to only install level 2 chargers or to install both level 2 and fast chargers, in that scenario, we find that there is limited benefit to installing both. Formally, the result here states that the cost benefit of using both is bounded by a factor of 2. Now, you might think 2 sounds like a lot, but I want to emphasize this is a theoretical worst case guarantee. In practice, we would expect the benefit to be much smaller. At the same time, we also find that in a network of locations, when we have multiple locations, The hybrid solutions, hybrid meaning solutions that leverage both L2 and DC fast chargers, can significantly outperform solutions that rely on only one technology, regardless of whether that technology is L2 or fast. Again, this is a theoretical worst case result, but it characterizes that the cost benefit of a hybrid solution in a network can be unboundedly large. Now, I won't say more about the theory, and instead, let's have a quick look at the results of applying this optimization to data in Detroit. For this, as I mentioned before, we used census data to estimate demand, and we used the machine learning model from the first part to identify feasible locations. On this map, or you see two copies of the same map, in the first, we're assuming a smaller value of alpha, which means, relatively speaking, fast chargers are not as expensive. And you can see, if you compare the two maps, there are some areas where we always want to install only slow chargers. So for example, on the left or on top, there we always want to install only slow chargers. But then in the denser areas, depending on the cost of fast chargers, we may either want to install fewer fast chargers or more slow chargers. On the real-world network, we naturally do not observe an unbounded benefit of the hybrid solution, meaning of a solution that leverages both, but we still find that the benefit can be meaningfully large depending on the relative cost of fast and slow chargers. So you can see this over here, that the cost benefit of using both types of technologies can be up to about 16%. And what we also looked at is, well, how does that vary with demand density? And as we vary demand density, it can actually get even larger, with the benefit of having a hybrid network getting as large as almost 30%. Lastly, we also assessed the benefits of having an integrated optimization solution. Here, we first compared the cost of greedily adding chargers, where they provide the most bang for the buck, to the holistic optimization our model solves. You can see that at a cost of 170, our solution meets all of the demand, whereas the greedy solution incurs a cost of 250 to meet all the demand, and at a cost of 170 only serves about 80% of the demand.
Super.
Got one more. Sorry.
One more.
We also considered the benefits of our integrated optimization and machine learning approach. So here we measured how many locations a city planner may have to survey when greedily considering one after the other without having access to a tool like our machine learning model. So you can see if one wants to really serve all of the demand, and one doesn't have an easy tool to figure out which locations might be suitable, the number of locations that need to be surveyed grows really very quickly, up to more than 1,000 locations, even though only less than 200 locations actually eventually would need a charger. I'll stop here. Thank you. I'm excited for the discussion with Tiya and Bhuvan.
Thank you so much, Dan. I mean, that's such a great theoretical foundation from the network perspective of how to really design this kind of optimal network for a city with this balance of DC fast charging and level 2 charging. Let me introduce Tiya Gordon, who's coming at this, I think, from a different angle. So Tiya is co-founder and chief operating officer of It's Electric. I will let Tiya introduce what It's Electric is, but let me just say this. Tiya started this company with the motivation of solving a very real problem. How will urban residents be able to charge? Literally sort of observing this is a problem, it needs a solution. And at the Mobility Initiative, we love to just engage and build this community of entrepreneurs who are solving real problems like this, in addition to folks like Tiya. Jeff Prosserman at Voltpost has some very interesting solutions. Camille Terry at Charger Help. These are all folks that we've engaged into our program. Tiya, it's been such a great pleasure to get to know you over the years. You've got some exciting news from Philadelphia. Let's hear your story.
Great. Hi, everyone. It's a pleasure to be here. As we've discussed, we're here to solve the issue of charging with a laser focus on densely populated cities. So I have a bit of a contrast in my headlines here in terms of what used to be the headlines that we were worrying about, how urbanites will charge, charging deserts in cities, to obviously the macroeconomic and geopolitical influences that we're now witnessing, as John covered in the start of our session today. So I always love to reference Matthew Rogers. He's an industrial designer whose work has brought us the iPhone and the Nest thermostat. And he's always said that when designing systems for behavior change, that there's certain principles that you have to keep in mind. One is that you have to mimic a previous behavior, and the other is that you have to make that new option better, easier, and more convenient than it was before. And I like to map that to EV charging. We want to mimic a previous behavior, but it's not the one of going to a gas station and fueling up. Instead, it's the same habit of plugging in your phone overnight before you go to bed. And second is that we want to make that option better, easier, more convenient. And so that's what we're doing. We're letting you plug in that phone, that car, but you're doing it right at home on your block. You're never going to a gas station again. You're never going to a destination again. I love that we have sort of an international perspective in all that we're talking about here. And I love to do a quick contrast on two similar cities in terms of population. That's London and New York City, roughly 8 to 9 million in terms of population. So London has 25,000 curbside electric vehicle chargers, all level 2. But here in a similar population in New York City, we have 100. The reason for this is that London largely does a lot of lamppost retrofits. But unfortunately, here in the United States, outside of LA, most streetlights only have single-phase 120-volt power, which requires upgrades to the utility main. And unfortunately, cities know this. So when they're writing their RFPs, major cities have excluded any kind of streetlight or lamppost retrofit from an applicable solution. They say specifically it's not possible due to power constraints and operational limitations, which often include the fact that many streetlights are powered on and off as groups, and they're turned off during the day. So we at It's Electric say, well, what power source do we have in the US that is ubiquitous in cities? And the answer is buildings. So what we do at It's Electric is we power public level 2 chargers from spare capacity in adjacent buildings. This allows us to solve this huge barrier of deployment in those densely populated cities for on-street charging, and we also avoid inter-utility connections and agreements. What we do is run a very simple conduit from that building just below the pavement to a public charger that sits on curbside. This allows us to pop up a charger very quickly and with a lot of agility in terms of where they can actually go. So our hardware is highly flexible. You can see an actual charger right here behind me. It's well on screen. And there's 3 different models that we're showing up here. We designed a charger that, of course, can use our sort of coined term of building power, but we can also do a direct utility connection. And more importantly, we can also pull from a utility pole. It's actually really challenging often to mount the charger on the utility pole because of engineering concerns, but we can also siphon that power there and still power that curbside charger from that power source. There's a great report from PGE that also includes the fact that less than 1% of actual utility poles can support the engineering of mounting a charger. So this is really important to think about when we want to utilize that infrastructure to help scale curbside charging in the US. And this is really, really relevant in a lot of key cities. So we have here in New York City, where I'm calling you from, something called the Green Rides Initiative, which requires that New York City's 80,000 rideshare vehicles, that's Uber, that's Lyft, that's TLC, be all electric by 2030. And Uber and all of their third-party research indicates that this is going to actually really point to being curbside as the unlock to achieve this. Because a lot of these rideshare drivers actually can't charge conveniently. They lose around 20% of their earnings when they're waiting in line for those fast chargers, when they're searching for those fast chargers. And if they have the option of charging, again, when they're off shift, when they're charging overnight, when they're sleeping, it allows them to adopt that EV a lot faster. And just to kind of paint a picture of what that looks like, here's currently where we have existing public, non-garage, non-behind-the-fence chargers here in New York City. So Revel, we all know, is a fast charging company. Flow is level 2 curbside. Those are those 100 charge points that I referred to earlier. When we contrast that with what will be the 80,000 vehicles on street in the next 3.5 years, we can see why we need so many more chargers here in a city like New York. And then we can kind of tie back into this idea of building power. So the current 100 chargers are the Canadian company Flow. Those are a direct utility connection. It's a very large piece of hardware, a lot of cable management, and those utility connections cost kind of around $180,000 per unit to install. If you compare that to sort of what we call our little sidewalk Band-Aid here, our orthoscopic surgery as opposed to open heart surgery, our building connected chargers come in around $12K per unit. Both of those examples include the actual unit hardware costs as well as the construction and installation costs. We have simple, fast construction. Again, it's just a small trench in the sidewalk that we tie back to the building. And because of that, we're also avoiding a lot of permitting timelines and slowdowns. So this is just a quick comparative study to show what a building power versus utility connected permitting process looks like in terms of time. So we're looking at, for us, a worst case scenario, roughly 6 months end to end. We can do it a lot faster as well. But when you're doing a direct utility inter-utility connection agreement, you're looking at that 18-month minimum in order to get there. So all in all, through this approach, cities get free infrastructure with its electric, buildings get a revenue share because we share revenue back with them because we are siphoning power from them, and drivers get affordable and convenient charging by putting chargers directly on public right-of-way where they're already parking. A little side note, we are the only detachable cable solution here in the US. This is not weird, just European. We're the first company to import this to North America. This is really needed right now because of the fact that so many cables are being consistently cut, or they're just being sort of, there's wear and tear, and there's degradation from freeze and thaw cycles that we're seeing in a lot of cities as well. So every time a city has to replace just that cable component, it can cost them $2,000 to $3,000. And this is just a CapEx component that cities aren't interested in being able to concern themselves with, given the outlay that they often have to face in even building these networks to begin with. And the other component that is great about a building powered charger is that we can deploy literally anywhere where there's a building and a curb. So we have the ability to have inbound requests from drivers. We can then map where that interest lives on our wait list and then use that to understand where we can then put chargers in, again, to really seek that high utilization that we need to make our model work. But here's the fun part. Utilization for level 2 charging on curbside does really well when you compare it with your statistics around behind the fence or private lot or surface lot level 2. You're not really going to a supermarket and spending 6 to 8 hours of dwell time in that parking lot. However, your car is parked on the street for 85% of your day. So it's really astonishing to see the high utilization that both measured pilots, there's only 2 measured curbside pilots in the US right now. That's New York City's pilot that ran for 4 years, our SF pilot that just concluded its 1-year anniversary. And in both cases, we're seeing up above 70% utilization for those chargers. When we compare that to London, it's really encouraging. Here's London from 2022 to 2025. We're seeing obviously an increase in that utilization, hovering up to 50%, but that's also happening in conjunction with the addition of new chargers. So it's scaling together, which allows us to understand that we can then recreate that here in the US, especially as we look at EV growth over the years. Philadelphia is our big news that we're really excited to share. We are now going to be working with the city to deploy what will be the largest curbside network in the country. It'll be starting this year. The first chargers will hit the ground likely late Q4 or early Q1 2027. And this is really important. In 2023 in Philly, there's around 9,000 registered EVs, and that share is growing 49% year over year between 2022 and 2024. If we continue that rate of growth, the current estimate will be around 20,000 EVs that will be registered by the end of the year. And then if we keep going up to 2040, that's around 300,000 EVs on the road. So the great thing about this is that we have those EVs on the road. A great portion of them will have home charging, but then we have to look at how many will rely on street. So we estimate that roughly 50% of all Philadelphia vehicles do park on street. And so today already there's unmet demand for almost 800 curbside chargers. So Philadelphia's estimate of around up to 1,000 is not far off from where they need to be as EV adoption grows. This is just, of course, talking about private vehicle ownership and not even responding to potential fleet vehicle ownership that's also there. Because guess what? Cities are dense with cars. We can just have as a simple example of a 450 long block in Brewery Town. We're seeing around 28 street parked cars. That's one car every 16 feet. And this gives us this captive audience, drivers that are parking on street that are looking to be able to also charge on street. So we've done some math here, and here's how we think about things. If we have people are willing to walk around a quarter mile comfortably to be able to reach that curbside charger, and our stretch is around a half a mile. So if we say that there's going to be X number of vehicles on the road in Philadelphia, and of those we're going to have in around 2,000 that are street parked. If we imagine just 3% of those are EVs, that's 65 vehicles that we can service with one charger. If it's 8% are street parked EVs, it's around 165 that we can service with one charger. And that's at our quarter mile walk shed. And obviously when we increase that to a half mile walk shed, it increases to where if we have just 3% of those street parked cars being electric, that's 260 vehicles we're serving with that one charger. And again, if we go to 8%, it's over 600. And even when we step down from high density to medium density, we still see really encouraging numbers. This isn't just limited to Philly. If we look at San Francisco, which has the highest adoption of EVs of any city in the country, we're looking at around 27,000 drivers without home charging. And it's because we have the ability to put chargers in those neighborhoods that we get really great responses from drivers that they were literally ready to sell their EV until they were able to find curbside charging that made it more convenient for them. So not only are we looking to bring in new drivers to the fold, we're looking to retain the EV drivers that already exist in the US and not have them give up because charging is so challenging. That's it for my presentation. I'm looking forward to your Q&A.
Super. All right. Thank you so much, Tiya. I'm going to just give you one question, then turn over to Jinhua for a question, and then go straight to the Q&A because I've seen a super active chat. So the question from my side is, you're trying to change a system, right? And you've identified who the stakeholder groups are within this system. You have city officials, you have building managers, you have EV drivers, you have utilities, and so forth. What have you learned about sort of incentives, and how have you structured your business model to give people the incentive to make this change? And I think what I'm fishing for a little bit here, which I find really great about your model, is the relationship with buildings. Could you say just a little bit more about what you've learned in that relationship?
Yeah, so the incentive for the city is that we can come in as a no-cost bid. So that really helps cities find a way to scale charging without it being a capital expenditure. The building's incentive is that rev share. So our single building that we've been working with for our pilot in San Francisco, to date, in less than a year, and then this includes time for ramp up of utilization, because I want to be clear, we were not at 70% utilization on month one. It took us about 6 months to get there. But even with that ramp up, that building's earned over $2,000 in passive income to date. And I will underscore that is not a reimbursement of energy and rev share. That is just the rev share component alone. And the incentives for the drivers, I'm sorry, is there someone asking a question?
No, please continue.
Okay. And the incentive for the drivers, of course, is that convenience. Our goal is to be less expensive than DC fast charging, more convenient, and of course, always less expensive than gas, especially these days in San Francisco.
And Dan, do you have any questions for Tiya or vice versa, just before I turn over to Jinhua?
Maybe one question that I'd have is, to what extent is the solution that you provide portable? So in the following sense, when installing an L3 charger or an L2 charger, generally in the way we think about it, connected to utilities, my understanding is that there's a really significant labor cost, which means that once you've installed it, you don't really want to move it anymore. I'd be curious, out of the $12,000 number that I think you quoted, if you decide at some point, hey, we don't want it in this building anymore, it's not getting the use that we thought, what is the cost, or do you have an estimate of the cost to then move it to a different building, assuming that there's a different building that's interested?
I mean, we wouldn't necessarily move it from building to building. You know, we make an investment in that neighborhood when we put that charger in. We imagine that our lifetime value of that charger is around 10 years. And so we actually, I'll answer your question with a slightly different answer. We are looking, even if we get lower utilization on that charger, we have other metrics that we measure around EV adoption. So when we're seeing utilization creep up from a very low number, when we're in a neighborhood where we specifically know there's low EV registration, we will compare those EV registrations into the future year over year to then demonstrate that we have more people than buying the EVs because they have access to charging. So we make that long-term commitment in partnership with the city to leave the asset where we've planned it and not to move it. We do it extensively. We have a fantastic planning team led by our project director, Judy Chang, who does all of our work in terms of all of the detailed planning of where these chargers should actually live. And once we make those decisions, we fix them for the duration of the contract to match the city. So that could be a 5-year duration, a 10-year, or a 15-year duration.
Tia, have you had any resistance from non-EV drivers saying, hey, you know, I don't want this thing, or it's taking up a parking place that I can't use?
Always, as they say, NIMBY will NIMBY. And so we actually, I don't have it right near me, but the usual pushback is that there's an assumption that someone's tax dollars went towards that charger. And so we actually made a very simple sticker of a cat that has a dollar sign for a collar, and it says, this EV charger costs taxpayers $0. We just do little simple things like that to just indicate that this is an opportunity for the neighborhood. And we do a lot of community outreach before we install as well. We make sure that people know that the chargers are coming, both through community board meetings, through flyering, through conversations, and then through presence in the neighborhood. What really happens a lot, though, is that the building owner becomes, in a lot of ways, an influencer, an advocate for its electric, and they proselytize for us. They spread the word, they spread the gospel, and they help get the word out because it's their frontage in a lot of ways. You know,
Yeah.
sidewalks are a gray area. It doesn't belong necessarily to the city, doesn't necessarily belong to that building person. But if that building wants that charger there, it's for good reason. And we always get emails from our building owners that they're so excited to see all of these people use the charger, that we also share with them when we send out quarterly payments. We also share metrics on how many gallons of gasoline they've helped offset. So it's really a community effort that we're building, in addition to the infrastructure. And we really refer to ourselves as neighborhood chargers because people really take that personally. We haven't, as you know, we're detachable cable. We distribute cables. To date, we've distributed over 500 cables just, since we got started about a year ago. Not a single driver has lost a cable, misplaced their cable. It's their access to freedom for charging, and they take excellent care of it, the same way that building owners make sure that the chargers are always accessible and available to their neighbors.
Yes, yes. I love the bring your own cable model. That's fantastic. And as you pointed out, common in Europe. Jinwan, do you have questions for Dan or Tia?
Yeah, just quickly, the number, Tia, you mentioned struck me. New York City have about 100. London have 25,000. How do they do that? There's like 3 order difference here.
Yeah, I mean, the order of magnitude is that London can easily retrofit lampposts because of the power capacity in the lampposts there.
Yeah.
So it's
That's done by the city systematically.
It's done by, no, there's private entities. Connected Curb is one, Chargy is another, which are UK-based companies that do the lamppost retrofits. But again, the United States cannot accomplish this outside of Los Angeles with ease because we don't have the right power capacity for our accessory power to retrofit a streetlight or a lamppost. So a lot of cities explicitly exclude that from their RFPs.
Thank you. Yeah, that's great.
Bhuvan, over to you.
Okay, a lot of questions. So let me just start with one for Dan. So Don McKinsey, had a few clarifications on the model. So he says that I thought you said earlier on in your talk, you mentioned that the optimization model has a constraint that all demand would be served Does this mean that all demand is served at some point or without having to wait? And does it include the costs of, waiting time? And yeah, so if you could just comment on that, the cost of waiting time and demand being served.
So we're not modeling the waiting time. We are modeling the sort of capacity of serving. So if you imagine there are people that want to charge 100 hours a day between each other in one location, they won't be able to do all of this charging, no matter how long they wait. There's just not enough time on the charger available. So we don't capture the waiting time. I think you also asked about the model with respect to unmet demand. Our model optimizes under the assumption, like when we optimize, we're constraining all demand to be met. When we look at a greedy algorithm that adds one station after the other, thinking just sort of in the moment, where can I get the most bang for the buck? That solution, when it's only added a few chargers, has not met all demand yet. So that was what we were showing on that plot.
So maybe a quick one. You mentioned the cost of L2 charger was 1 and DCFC was alpha, and then you did the optimization on that. Was there any cost because the electricity cost at DCFC is almost 2 to 3 times that of a level 2. So was that part of your optimization model as well, or it was just on the cost of the equipment and not on the what the consumer is paying?
We did not incorporate that. We also have to say that even getting a reasonable ratio for the cost between L2 and L3 has proven to be quite tricky. I asked Google Overview to give me an answer yesterday, and it gave me a range for L2 between 4,000 and 15,000 per port. And for L3, it gave me a range between 50,000 and 250,000, which, if you think about it, that would give me an alpha range between something like a factor of a 10 and more than 80. Like it's hard to really nail it down. And then there's also its electric charger, which I guess would be even cheaper.
Yes. So on the topic of its electric, Tiya, a few questions for you. A lot of questions on the cables, obviously. So first one is, do your cables lock on both sides when active? And is the O&M and the cables, that's the responsibility of the car owner? And what are the typical annual maintenance costs per charger? So just some quick ones.
I might need you to refresh me on questions 2 and 3, but I'll start with 1. Yes.
Is the cables lock on both sides?
Yeah, cable locks on both ends. When the car is actively charging, the only way to disengage the cables from their locked position is to unlock the vehicle. We're shocked that we haven't had any cable tampering or vandalism in any of our cities. Honestly, we were anticipating that to be part of our maintenance that we had to take on. We have not had a single issue of cable vandalism since we've deployed as the only detachable cable solution in the US. It's Electric distributes cables to drivers. This is just part of our customer acquisition and our customer acquisition costs. However, we will start seeing the cables come from the vehicles as they do in Europe. We will be working with our first OEM partner that will be announced later this month, where the cables will be distributed by the OEM and not by its electric.
Okay, and typical annual maintenance cost per charger, ballpark?
Oh, it's extremely low because the chargers are really designed, I hate to say it, not to fail. So there's nothing on board the charger that is the usual part that is available for failure. So we actually build it, it's modular like a Lego. So if the charger unit fails, there's no parts that need to be ordered, there's no trucks that need to be rolled out, there's no evaluation. The whole unit is just removed and put back on. So we build our annual maintenance costs into our model, which is internal, and it doesn't affect the city.
And there was a question on credit cards and smartphones. So do you need a smartphone and scan a QR code and download an app? How does that work?
You can activate the charger through your smartphone or through an RFID, just a simple card that you carry in your wallet that we provide to you, or via tap to pay with your credit card.
Okay, that's great. So some questions about queuing, right? So everything around EV charging involves queues, and Tesla's recently launched a virtual queue as well. So is it on a system, or who gets access to the next charger? And do the building owners seek or receive preferential charging rights for its electric charger?
It is a public charging, sorry, it is a public parking space. So
Right.
there's not a reservation system that exists in any cities just now. For us, it's very simple. We already have that built into the software. We just literally turn on reservations and it can be made. But the cities would need to get to an evolved mindset to want to allow those public parking spots to be able to accept reservations. It's not unheard of when you look at car share. Obviously, there's reservation systems that exist there for on-street parked zip cars. So I do see a world in which once we become more mainstream, that cities would want to look to be able to allow this to help with queuing.
So moving on to utilization, you showed the slides with the excellent utilization, which is much more than any other EV chargers that data that I've seen. So is it high because the vehicles park all day or all night? Is there a sort of penalty that you have to pay after you finish charging after 4 hours or something like that?
Sure. So the utilization on curbside, again, London at 50%. They've been doing this for a good 8 years longer than it's been happening here in the US. And then New York and San Francisco is the only really studied cities at close to 70, is because you're putting the chargers where the cars are already parking. You're putting them where they already are obtaining that long dwell time for that overnight full 6 to 8 hour charge. So it's very easy for us to capture that utilization when the cars are already parking there. The low utilization for L2 historically in the United States is due to the fact that you're measuring against a destination charger. So no one wants to leave their car in a parking lot for a Trader Joe's or a Walmart overnight, but they will leave their car in their neighborhood while they charge overnight. And that's the difference to understand critically when you're measuring L2 utilization here in the US. And you may see deplorable numbers from Gen 1 of L2 versus what we're now seeing for curbside because of the ubiquity that's being made possible.
The last one, though this may take a while to answer, this is more about the curb management. So, what was the curb being used for, and what else can it be used for? So, Amir Brudner made an interesting point that it's like an externality tax, taking up per curb space as a cost on others who search more for parking and cause more congestion. In New York, like 30% of the miles are people searching for parking. So because you're taking this one parking space away, any thoughts on that, given that you're New York based, and this must have come up in one of your tech town hall meetings or something.
Sure. I like to say that we don't take the curb, we don't take the space away. The space is still there. We're just using it for charging. But I like to think about curb management a lot. I like to think about how this is not just for charging an EV. We are working with the state of California to make our chargers bidirectional. So we'll be able to have the chargers be able to be pushing energy back into the grid when drivers opt to do so, and we pay to do so from the utility, from PG&E in California in 2 years. So you want to think about these spaces as curb opportunities in cities. So again, it's V2G, but also let's think about solutions such as refrigerated trucks. The biggest noise complaint in New York City is these reefer trucks that are parked and they're idling and they're just running nonstop. Once those trucks can go electric, we can then allow them to basically be plugged in while they're doing loading and unloading. So we can move this into sort of loading zones, understand how we can provide electricity during those mechanisms. Believe me, I'm a cyclist, as you are, Bhuvan. I don't own a vehicle. I would love to live in a car-free city. We are not there yet. So as we work to make that transition to less cars, we also want to make sure that all cars move from being internal combustion to electric. And the only way to do that is to make sure that they have a place to charge.
That's a
Great
great
answer. Over to you, Chinua.
point. Yeah, it's one already. So everybody, please join me. Thank Tiya, Dan, and Bhuvan for today's presentation. Thank you so much, guys.